So, welcome everybody to our Gamma seminar. This week we have the pleasure to guest Ian Anderson from the Utah State University, who is going to talk about superposition formulas for differential systems. This is the first part of a two-part seminar. So thank you, Ian, for accepting our invitation. It's really, really, really a pleasure to have you here. So please go ahead. The floor is yours.
Okay, thank you very much for the invitation. Many years ago, I wrote a paper of this title, Superposition Formulas for Differential Systems. I'm very happy to talk about that paper today and next time. Since we wrote that paper, we've had quite a few applications of the results in that paper, and I'll talk about some of the applications more next time. So let me begin by saying what our goal is, and the excuse me, and the goal is to explain the following theorem. So there's lots of symbols and notation here, and all of that's we're going to explain as we go forward. So our hypothesis for this theorem is we start off with a distribution on some manifold. And we're going to assume that this distribution decomposes into a direct sum of two sub-distributions, which I call delta hat and delta check. So for example, in many of the applications, this will be a rank 4 distribution, this one will be a rank 2 distribution, and this one would be a rank 2 distribution. And this direct sum decomposition has to have the property that when you bracket a vector field in this distribution with a vector field in this distribution, you stay inside the big direct sum. And this condition, we say if this is true, we call the distribution delta a hyperbolic distribution. So a hyperbolic distribution is a distribution which admits this direct sum decomposition and satisfies this property. The next notation in this theorem is this delta hat infinity. This is the smallest integrable system containing delta, and it's easily calculated from the derived flag. So we'll go into more details on how you calculate this a little bit later. But the hypothesis says calculate this terminal derived flag, hat, intersect it with the check distribution, and require that that be the zero distribution, that the intersection be essentially empty. What this means is that this derived flag distribution cannot get too big. If it gets too big, then this intersection will be non-empty. And we require the same condition on the terminal derived flag of the second distribution. If these conditions hold, we say that the delta is Darboux integrable. Darboux integrability is a very important technique for the exact integration of partial differential equations. It's the accumulation of a long sequence of integration methods, starting with the method of Laplace and then the method of Monge-Ampère and various other ideas. The definitive text on this was written in Goursat, Lessons on Second Order Partial Differential Equations. In that text, the definition is slightly different than what we've given here, but it's equivalent to the classical definition, and we'll talk about that later. So these are our hypothesis, a distribution which breaks into two pieces, and these conditions on the derived flag. And the conclusions come in two pieces. Here's the first conclusion right here. That from this data, I'll put it this way, you can find there exists another distribution, V hat, and another distribution, V check. These are smaller in rank than the original, and these manifolds are smaller in dimension than the original. So you can find two, I would say, simpler distributions, V hat and V check. And this is constructive. And it's very easy to construct. The second part, and this is the big surprising part, so we'll put an exclamation point here. The surprising part is that from this data, one can construct a group which is acting on these, a Lie group, finite dimensional Lie group, which is acting on these two manifolds. And it's a symmetry group of V hat and V check. So we say that G is a common symmetry group of these two distributions. Don't worry if you're not familiar with all these terms. The purpose of the lecture today is to explain all this stuff in some detail. So part one of the theorem is you can find this group. This is quite surprising because there's no mention of a group in the start. There's nothing group theoretic about the hypothesis. The next part of the conclusion is what you do with this data. So with this data, you find the Cartesian product of these two manifolds, this one and this one, and you quotient it down. You construct the orbit manifold, construct it by taking these two, the cross product, and quotienting by the diagonal action, and that's going to give you a new manifold, which we're going to call M tilde. All the constructions that we do are all the constructions that we do in this talk and in this work are local in nature. So we tend to talk and write globally, but we think everything is local. The second part, and this is we'll focus on in the lecture next time, is we take the sum of these two distributions, the direct sum, and we quotient this distribution down. This operation here is called symmetry reduction. So we do a symmetry reduction using V hat, V check in this group. All of this data is fixed from the original distribution delta that we start with. And then the big theorem is that the thing we started with, the manifold and the distribution we started with, is locally isomorphic to this quotient distribution. So we started with this delta, and we end up with a realization of this delta as the quotient or symmetry reduction of a pair of distributions. And the goal for the seminar today and next time is to show how this equivalence here can be thought of as a superposition formula for the original differential system delta. It's easy to see how this is going to go. What we're going to do is we're going to build the integral manifolds or solutions to this differential system from a solution of this differential equation and a solution of this distribution right here. Was there a question?
Yeah, I am. I have a couple of questions. The first one is delta can be any distribution. It can be the total, the tangent space of manifold. Yeah, there is no restriction about that.
It should be. It should have. It's derived flag. It can be anything, but I would say that the derived flag of this should be. This should be bracket generating. So this should be the whole space.
The whole, yeah.
Yeah, and so yeah, so if you took delta, so that's a good question. If you took delta to be the whole tangent space, then the tangent space is an integrable distribution. This thing here, it's derived, well, its derived flag would be the whole thing. So then in this case here, this decomposition would not be unique. You could decompose the tangent space into two subdistributions any way you want. So, but in general, when we're studying certain types of differential equations, especially the classical cases, this distribution, this decomposition is unique.
But you know, I am sorry that I disturbed you, but this construction looks a lot like something that some of people here studied that are called K-contact distributions. And indeed, this thing, the delta hat and the delta check, they have certain names. One is called the red distribution, the other is the K-contact distribution, and it pretty much seems that they satisfy all the properties you wrote. So it seems quite interesting. And by the way, do you have any particular examples, like a disclaimer of this structure? Yes, to know where this construction may appear. Can you tell us some examples in geometric stuff or?
Sure. We'll have lots and lots of examples of this.
Yeah.
Okay, as we go forward.
Okay.
Okay, so that's the goal. So let's now go back to the very beginning. Okay, and so very interesting to hear that there are some connections with some other things. Okay, so here's the outline for presentation. We're going to talk about some things which I think are very familiar to people, but we'll go through them anyways quickly. Contact systems, how you take a differential equation and encode it as a distribution. Some examples of this, some basic definitions, more examples, Darboux distributions, more examples, Vecchio distributions. These are my V hat and V check, and more. And then next time probably we'll talk about the symmetry reduction. Okay. So the story begins with a quick review of what we call jet spaces. And the simplest example of a jet space is called the first jet space of curves from one-dimensional curves into R. So we write here X, U, and U1. So this is a three-dimensional manifold. On this three-dimensional manifold, and what makes it into a jet space, we have this one form, du minus u1 dx, and this is called the contact one form. This is called the contact form. Okay. And then if we take the annihilator of this, often written as C perp, this is the set of vectors x such that x hook C is equal to 0. So it's the set of vectors which hook with this to give 0. This is called the contact distribution. This is called the contact Pfaffian system. Just think about what this form is doing for us. If we think of our space this way, x, u, u1 sits over x, y, and that's 6 over x. If we take a curve here, a lift from our independent variable into our jet space, so we'll take that to be u equals f of x, u1 equals g of x. So if we take an arbitrary lift, maybe we can call that sigma or something like that, and we pull this lift back, pull this one form back by this, we're going to get du, that's d of f minus g dx equals 0, and set that equal to 0. That tells us that g is equal to f prime. So this contact form has the effect of telling you that you should think of this third variable here, u1, as a derivative of the second variable, at least when you evaluate on sections. So that's the simplest contact system that there is. Then we can look at J2 from R to R. That's a 4-manifold. And the contact system on this 4-manifold is given by du minus u1 dx, du1 minus u2 dx. And that's telling us that on solutions to this system mean that u is a function of x, this is the first derivative, and this is the second derivative. And again, the annihilating subspace, if this is 2 dimensions and we're in 4 dimensions, the annihilating subspace will be a 2-dimensional distribution, which I've written down right here. So this is often called the total vector field. Applying this vector field to a function is like differentiating that function along solutions of the distribution. One more. Here's J3. This is a 5-manifold. Okay, and its contact system on J3 consists of 3 forms, and the annihilating distribution, the contact distribution, is this total vector field here, and one more vector partial x3. So one of the things I've learned over working on this a long time, this is the form version of jet space, and this is the distribution version of jet space. Of course, I think we all know that Cartan emphasized the exterior differential algebra, the differential form approach, whereas Vesio, who was a collaborator, kind of emphasized the distribution approach to things. Early on, when I was working on this subject, I kind of focused on the form approach. Now I kind of think about the distribution approach a bit more. The truth of the matter is you have to work with both all the time. Sometimes a formula that you have in Pfaffian systems is easier. Sometimes the distribution formula is easier. You just have to be willing to jump backwards and forwards and not lock into one formalism or another.
Sorry, Ian. Have you
Yes.
tried some of the first order jets, for example, from R to R5, and try to describe the Cartan distributions in that case and related to this construction? Have you tried something like that? Anything like that?
Yeah, I think so. I think we'll see. We'll see in a minute.
Right, because it's what you have showing here, it's not exactly, but it's very related to this K contact. I mean, it's something very similar.
Okay. Okay. So we're going to need jet spaces in more than one independent variable. So here we have two independent variables, u. The contact form in this case is this one form du minus p dx minus q dy. And on solutions of this, or if we look at sections where this is 0, it's telling us that p is the x derivative of u and q is the y derivative of u. And this now, we're in 5 dimensions here. And now the contact form is a single form, and its annihilator consists of 4 one vectors right there. So this is what we would call the Cartan distribution on the one jet space. Oh, there's a typo here. This is R2 to R. And we're going to need, well, we're going to need a bunch more as we go forward, but here's one more. This is the jet space from R2 to R. It's 8-dimensional. X, Y, U, P, Q, R, S, and T. And this jet space, the contact system on this consists of this form. It consists of one form for dP minus R dx minus S dy. That's telling us that R should be thought of as the second x derivative. S should be the mixed partial, and T should be the double partial with respect to Y. Okay, so this is a contact system in the Pfaffian system of rank 3. The annihilator here consists of 2 total derivative operators right here. The x total derivative operator and the y total derivative operator. Okay. So that's a little bit of a quick introduction into jet spaces. This can all be generalized to the jet space of an arbitrary fibered manifold, but we don't need that so much.
Yeah, and I think there's a typo on the first vector field in that last delta. Should have an extra term.
This one here, what should I
Yeah,
have here?
plus
Probably
SDQ.
Plus
Yeah, sure.
Thanks,
Good.
Tom. Okay.
Sure.
So now let's see. I think that's it. Okay. So now we want to apply this construction to differential equations. So I've written down here an arbitrary system of differential equations in n independent variables, m dependent variables. I don't know how many derivatives there are, so the order of this could be something, r, and it may be, I don't know how many equations I have either. So this is completely general. I could have more equations than unknowns. I could have fewer equations than unknowns. Could be overdetermined or underdetermined. The only requirement I'm going to make is that this 0 set defines a submanifold in some jet space. So if the equation's of order k, then I want to think of this system of equations as defining for me a smooth regular submanifold inside of this jet space. So that's the absolute bare minimum assumption that we need to make. All kinds of, and then we're going to define the standard Pfaffian system for this system of differential equations to simply take the Cartan system, take the system of contact forms on this jet space, and pull it back to this equation manifold. And we call that the standard Pfaffian system for our differential equations. Now, this construction is very general, as I stated it, and there's all kinds of interesting questions that arise regarding the integrability conditions that might arise from this, the degree of generality of the solution. So in this degree of generality, there's a lot of questions that you can ask, and they certainly form a Cartan-Taylor theorem, for example, and they certainly form an important part of the general theory of geometric approach to differential equations. This is not going to be of concern to us in this presentation. The equations that we're going to look at here are very simple, and this construction is very simple as well. So let's begin with some examples. So the very first example would just be a single second order ODE. So my contact system, whoops, C. So my contact system that I'm starting with would be du minus p dx, dp minus q dx. So that would be the contact system on J2 of R. And now Q represents the second derivatives of U. So if I want to pull back this contact system via this differential equation, that simply means replacing Q by the formula from my differential equation. Okay, that's all I have to do. And then I'll take the annihilator of that, and I'll get this single vector field, total derivative vector field, dx plus p du plus f, where this f is coming from my differential equation. Okay? And that's perhaps the simplest example of how you take a differential equation and construct from it a Pfaffian system or dually a distribution. The next example is an underdetermined example. So I want to start off with a unknown function z. There should be a z in here somewhere. I'll put a z in here. And the first derivative of z is some expression in terms of x, another function y, the first derivative of y, and the second derivative of y. So this is an underdetermined system. Such underdetermined systems often show up in control theory, where the z is the state variable and y, I think, is the control variable. So you choose y and use it to drive the direction in which you want z to go. Solving this equation is not a problem. You simply pick y to be any function you want and then integrate the resulting ODE to get z. So, however, it may be very simple from a differential equation, solving differential equation point of view. These systems of equations have an incredibly rich history, and they're going to be very important in the theory that we're going to develop in this lecture and the next. So here I have a 5-manifold. So I'm going to start off with the following contact system. C is going to be dz minus z1 dx, dy minus y1 dx, dy1 minus y2 dx. So there's my contact system that I'm going to start with. And then just as I did in the ODE case, I'm simply going to replace z, this z1, which is to be thought of as the derivative of z with respect to x. I'm going to simply replace this by my formula for my Monge equation, and I'm going to have dx minus p, dy minus p dx, dp minus q dx, and then this is my third form right here. So this is here, and here's the dual version of it as a rank 2 distribution. So delta, the rank 2 distribution on a 5-manifold. And this case here was studied in detail by a very famous paper of Cartan Often you just have to say Cartan 1910, or he also called it, since there are 5 variables in this this Pfaffian system is defined on a 5 manifold, this is often called the 5 variables paper. And it's famous for a number of different reasons. We'll see a little bit of that later in the lecture today. The important topic for us will be second order differential equations in the plane. So scalar partial differential equations in the plane. You can write them this way. Solving for, say, the second derivative with respect to x, we get the following expression for our differential equation. And the contact system there is J2.
Excuse me.
R2R, yes.
So for the Monge equations,
Yeah.
do you set any general condition on F? Because for the Cartan 1910 paper, I think he requires that the second derivative of F
Yes.
by
So
Q
generally,
is
right.
Right.
So he does both. But as you're right, as you say, you're correct. The interesting case is, and we'll see that in a minute, is to require FQQ not equal to 0.
Right. Thank you.
Okay. If FQQ is 0, well, it's still an interesting differential system, but it happens to be the contact system. Okay.
Right.
So you're absolutely correct. Okay. For second order ODE in the plane, we have our general formula looks like this. Here's our contact system in, if I had an R here, this would be our contact system on J2 of R2R. And all I have to do is replace R by this expression right here. And I get my Pfaffian system. And here's the annihilating space, which is the distribution I want. So for us, this is this is a rank 4 distribution on a 7 manifold. Okay. A special case of this, which we'll focus on again a lot in the next talk, is equations which are called F-Gordon equations. It's a parody on the Sine-Gordon equation. So this equation here is called the Sine-Gordon equation. It's very important in differential geometry and integral systems theory. If we replace sine by an arbitrary function f, then we're going to call this the F-Gordon equation. Here again, this is here's the Pfaffian system for our F-Gordon equation, and here's the dual distribution. Again, it's a rank 4 distribution on a 7 manifold. Okay, and just one more example. This was the subject of Cartan's 1910 paper. He was very interested in this. How do you integrate an overdetermined system of equations like this? Well, what happens is it's now you now have 2 equations cutting out a 6-dimensional manifold. So the Pfaffian system now, we started with jet space, which was 8. We have 2 equations that cuts us down to 6. And here is the distribution in Pfaffian system for an overdetermined equation. We'll see a little bit more of this in a little bit later on. Okay, so I want to make one simple remark. This is very important for us computationally. And it's this remark right here. Once we've encoded a differential equation as a Pfaffian system, it may be convenient to introduce new coordinates. And those coordinates might not be adapted to the jet space in any sense at all. They may be simply coordinates that make the form of the equations easier to work with. In particular, I do a lot of computations using maple or symbolic methods. And when you're doing symbolic methods, you really want to work with rational functions as much as you can. And square roots, even though you can handle with them, eventually you're going to get into, you can have some computational difficulties if you get into non-rational functions. So I just want to mention, here's a very simple example. Differential equation, ux squared plus uy squared equals 1. How should we encode that as a Pfaffian system? Well, I should solve for one of these variables. Oh, that should be x. So let me solve for uy. So uy would be 1 minus ux squared. And then here what we would call the standard Pfaffian system for that equation. But I think it's easy to see that what we could do to clean this up a little bit is replace ux by cosine x, in which case uy becomes sine y. So we can write our differential equation this way. And the dual distribution is this. So here's a simple example of a Pfaffian system. It's given this way. You encode it as a differential equation. You introduce new coordinates to simplify some of the formulas. Oops. Whew. Okay, here it is here. This example is in the classical literature sometimes called the Goursat equation. That's not very useful because there's hundreds of different equations in the literature that always seem to have the name Goursat attached to it. But Goursat did write a paper dealing with exactly this kind of equation. And this equation will be very important in the story that I want to tell. This is part of a family of differential equations. So in general, you can look at this family 2n over x plus y, square root of ux, uy. And it's this family of equations which plays an important role in the theory of Darboux integrability and the superposition story that I want to tell today. So here is the standard Pfaffian system for du minus p dx minus q dy, dp minus r. This is called s, uxy is called s, so I substitute in here, and I do the same thing for dq. I substitute in the equation here. So here's the standard form for the Pfaffian system. Now I want to do a diffeomorphism, so I'm started off in coordinates x, y, u, p, q, r, s and r, r and t. So those are my original coordinates. And now I'm going to make just some new set of coordinates, x, y, capital U, capital P, capital Q, capital R, capital T. And the change of variables I'm going to make is designed explicitly to get rid of this square root. I'm going to let P be capital P squared and little q be capital U squared. If I formally differentiate this relationship with respect to x, so I might get r equals 2p times a new variable r. T is 2 times q times a new variable t. Then I'm going to pull back this set of formulas, this set of formulas by this diffeomorphism and write my differential system this way: d capital U minus p squared dx minus q squared dy. And I get this differential system. I can actually cancel off a p on all these terms, and I can actually cancel off a q in all these terms. And I get a differential system which is, of course, geometrically equivalent to the one I started with, but which is computationally easier for us to work with. Okay. And one more.
By the way, I'm not
Yes.
disturbing you because all these examples are very, very interesting, and I think that in the following, as you will develop these things, you will talk about the delta check, delta hat, and all this stuff.
Yeah.
But I just want to tell you for my colleagues that it's only about superposition rules. I'm taking a look at this, and I'm noticing that differential geometry structures called maximum integrable distributions, K-contact distributions, and things like that, they are very related to this you are doing. And I pretty much think that when you will get to the delta check, delta hat, you will describe something called polarizations or supplementary to polarizations we use. I don't know so far, but I think that it's very interesting to us this for several reasons, not for only system superposition rule, but also geometrically. And all this stuff reducing jet bundles to submanifolds given for differential equations and reducing the FAF system, they have a nice picture in modern differential geometric theory. So it's very interesting for us, I think. Thank you.
Okay, good. So we continue this discussion for sure. Okay, here's one last example. This is again goes back to Goursat. And he says the following. Start off with the following equation: r plus 2 lambda s plus lambda squared t plus some function of x, y, u, p, q. So here's our one jet variables and some parameter lambda. Okay. So what he says to do is don't work with this equation by itself, but take this equation and its derivative. So if I take this equation and its derivative, I have a system now of two equations. I can eliminate lambda from these equations, and that would give me a PDE in the plane. I can differentiate yet again and get three equations. Eliminating lambda now gives me a system of overdetermined system of two equations in the plane. So I just want to illustrate this with a simple example. So if we take psi to be 1/3 lambda cubed, we get these two equations right here. If r plus 2 lambda s, 2s plus so and so, so we have these two equations right here. If we eliminate lambda, well, the best way to eliminate lambda is to pass this system of polynomial equations to a Gröbner basis. And that Gröbner basis command software will eliminate lambda from us, and we'll get this horrendously complicated differential equation. There's no way you can analyze the geometry of this differential equation directly. It's absolutely essential that you do so in terms of this parameterization. So you use lambda as one of the coordinates on your manifold. If you go one step further and differentiate again, then you'll get this overdetermined system at ux y equals 1/2 u y squared, and u x equals 1/3 u y cubed. You'll get this system of equations, which appears as one of the first examples again in the Carton 1910 paper. Okay, so we've done two things so far. We've introduced jet spaces, and we've talked a little bit about how you encode jet space, how you use the encoding of jet spaces to encode differential equations as Pfaffian systems and distributions. So here are the basic definitions that we need to review: the derived system, the derived flag, the growth vector, integral manifolds, first integrals, symmetries, and Cauchy characteristics. So I'm sorry that that's kind of a lot of things to do, but this is the standard language these are the standard concepts that we use to study the geometry of differential systems. The derived system, we'll begin with that. You take all the vectors in your distribution, you bracket them again. In general, this will be a differential system which is larger than the original one. We call that the derived flag. If the derived system, if delta is given by the span of some vector xi's, then delta prime is given by the span of the original vectors and all possible brackets. So this is, again, all you need is a computer algebra system which can take Lie brackets, and you can compute the derived system. The derived flag is the iterated derived system. So we start off with a distribution, we calculate its derived flag, delta double prime is the derived flag of the derived flag, and so on. At some point, you might fill up the whole space, or you might get to a point where this stabilizes so that the derived flag of the kth derived flag is the same. If this is true, then we call delta k delta infinity. If the derived flag of the derived flag is the same, then that means this thing is an integrable distribution. So this is what appeared in our definition of Darboux integrability. It's the terminal derived flag of one of those subsystems. In this literature, people often refer to the ranks of these, the derived flags. So the rank of this distribution, the rank of this distribution, the rank of this distribution is called the growth vector of our original distribution.
Sorry, Ian, the growth vector may depend on the point, yeah? Even when the
It may
distribution
depend upon,
yeah.
It may depend upon the point, but we have a caveat that all bundles, or all this, let me rephrase that, all distributions
are regular, yeah?
have constant rank.
Ah, okay. So
Okay,
so yeah.
So you know, so it's a very important subject to talk about things which are for which these ranks may be changing from point to point, but that's not the focus of what we want to talk about for our superposition principles and so on. So quite often you'll calculate it. I have lots of examples where you calculate this derived flag, and it doesn't stabilize. You may have to cut out some points. So maybe you'll have to cut out the point where P times Q is equal to 0. So maybe you'll have a point, you'll calculate this derived flag, and you'll see that when P is 0 or Q is 0, this derived flag changes dimension. So we just cut out that point right away. So and proceed from that. Or we leave the analysis of that case to somebody else. There are people, definitely a lot of people who are interested in this. Okay, so the next definition is the definition of an integral manifold. So if we have a Pfaffian system omega and it's defined on a manifold M, then an integral manifold is a mapping from P into M, such that when we pull back the Pfaffian system by sigma, we get 0. Or put it another way, here's our distributions. We can think of our deltas as being a bunch of planes, and then an integral manifold is going to be just some kind of surface inside that space, which is everywhere. Yeah, terrible picture, try again. We have our distribution, and then an integral manifold might simply be a curve whose tangent vector everywhere lies inside our given distribution. The Cartan-Taylor theorem is an important theorem in the geometry of differential equations. It tells you what the maximum dimension integral manifolds can be. That, again, that's not so important to the discussion here today. What is very important is this notion of first integrals. And this definition generalizes the usual definition of first integral. So we have a second order differential equation, I don't know, x double squared plus x squared equals 0. Then what is it? X dot. What do I want to say? If we have a differential equation x double dot equal to 0, then x dot is called the first integral because its derivative is 0 by virtue of the equation. And so here's the differential systems definition of that. A first integral is a function on our manifold whose exterior derivative is in our Pfaffian system, or equivalently, a first integral is a function which is annihilated by all the vector fields in our distribution. Why are first integrals important? Well, they're important for a number of reasons, but the most important thing is first integrals are constant on integral manifolds. And therefore, if you want, you can take your differential system and restrict it to the level sets of the first integral. And this is something that we will do in our construction of our superposition principles. We're going to write down some differential systems. We're going to find they have first integrals, and then we're going to restrict those systems to the level surfaces. Okay. Symmetries, I think, again, most people know how that goes. We'll do the distribution version. So we have a distribution on a manifold. A local diffeomorphism, M to M, is a symmetry. If when you push forward the distribution at some point X, you get the distribution at the image point. An infinitesimal symmetry is a vector field X on a manifold such that the lead derivative of the distribution is inside the distribution. We're going to see if we have time afterwards, after the seminar, to talk about how you can calculate symmetries pretty easily with Abel. So Abel does a great job of calculating symmetries for many, many examples of distributions. A Cauchy characteristic is a vector field X, which lies in the distribution and is a symmetry. The important property of Cauchy characteristics is if you have two Cauchy characteristics, then their bracket is also a Cauchy characteristic. Okay, so here we have our first sort of theorem of the day. I'm going to take our standard contact system on J3RR. Okay. I'm going to calculate the derived flag. That's pretty easy to do. It's simply the bracket of this and this, so I'll get this system. The second derived flag is here. The third derived flag is here. So the growth vector for this distribution is 2, 3, 4, 5. Secondly, you can see, since by construction, the bracket of this vector and this vector is this vector, we can see that this right here is a Cauchy characteristic. And we can see that the next derivative, the second derived flag, has two Cauchy characteristics. And in fact, I think people know this, we have a theorem. If we have a rank 2 distribution on a 5 manifold, and we have this numerical data, the growth vector is 2, 3, 4, 5, and we have a Cauchy characteristic here and two Cauchy characteristics here, then that's an intrinsic characterization of the contact system. Okay. For partial differential equations in the plane, I'm going to go through this a little bit faster. Again, here's our distribution. I can calculate the derived flag, the second derived flag, and I find that the second derived flag has, the first derived flag has two Cauchy characteristics. And again, this gives us a characterization theorem. If we have a rank 4 distribution on a manifold, if the derived flag goes up by 1 and then up by 2, up again by, the derived flag goes up by 2 and then by 1. If this has no Cauchy characteristics, but the derived flag has two Cauchy characteristics, then this abstractly defined rank 4 distribution is actually the standard distribution for some partial differential equation in the plane. These kind of theorems are going to be important to us because when we do symmetry reduction of our differential systems, we'll get some new kind of differential system. And if we want to identify it with a partial differential equation in the plane or some other kind of differential equation, we need these, I call these recognition theorems or realization theorems. We need to know when a differential system comes from something. Here's another one. So Monge equations. I'm going to start with my Monge equation. The derived flag is here, and as we pointed out earlier, the growth vector is 2, 3, 5 if the second derivative in the last coordinate is non-zero. There's no normal form for this is a generic case. There's no standard form for easy standard form for Monge equation, but we do have the following theorem, important theorem. Suppose we have a 2, 3, 5 distribution. Then there's a fundamental invariant due to Cartan called the Cartan quartic. You can hardly write it down. You almost need a computer program to calculate it. All these coefficients here are very complicated functions of the original equation of the function f used to define the 2, 3, 5 distribution. And we can say that if this fundamental invariant is 0, then the distribution is this famous equation called the Hilbert-Cartan equation. And we'll see examples of this as we go forward.
Sorry, I am. Can I
Yeah.
make you a question? Can you solve the example of the previous page? Can you go up a little bit about the system where you describe the characteristics of the delta prime before? Yeah, a little bit. Yeah, where it's partial s, partial t, a little bit up. Yeah, it's quite interesting. The partial s, partial t, the characteristic delta prime is maybe a maximal integrable distribution of delta. Yeah.
Yeah.
It's there is some way of relating these things because it looks like something called in geometry polarization that appears with this distribution. So do you know anything about that?
No, I'm sorry. I'm going to have to read up on this before the next seminar.
Okay. Thank you.
Okay. So here's a summary of where we're at. We talked about jet spaces. We talked about contact systems, PDE in the plane, Monge equations. And for each case, we were able to obtain some kind of geometric invariant characterization using derived flags and Cauchy characteristics. So that's why these derived flags and Cauchy characteristics are so important to us. They help us understand the when a distribution is a standard distribution of some kind of differential equations. Okay. Let's see. What's happening here? It's not so good.
Oh.
Something's happened. I'll go to my backup version here. Okay. Okay. So now we're ready to talk about our hyperbolic systems. Okay. So we start off with a distribution delta. We're going to assume that it's a direct sum, and we're going to assume that the bracket of these two pieces is back inside delta. And the important point to make is the obvious point, namely that the growth vectors for these two subdistributions tell us a lot about the original distribution delta. So we're going to try and study our hyperbolic partial differential equation by studying these two subdistributions. And what's going to be important to us is the first integrals of delta hat and delta check. So we're going to look for functions f for which x hat of f is equal to 0 for x hat in delta hat infinity, and first integrals of delta hat or delta check are called intermediate integrals delta. So this term intermediate integrals refers to, in the classical literature, there are intermediate integrals, complete integrals, there are all kinds of different integrals that they talk about. Intermediate integrals are always defined as first integrals of some invariantly associated subdistribution. Okay, and then the important thing to note is by the Frobenius theorem is the number of intermediate integrals you have is the dimension of the manifold minus the rank of the terminal derived flag delta hat infinity. Okay, and now we can talk about Darboux integrable distributions. So again, it's a hyperbolic distribution. There's our condition of hyperbolic. And now it's this condition here that we had on the first slide. We want this distribution to intersect with the terminal derived flag of this one to be empty. We're going to let I hat be the first integrals of delta hat. We're going to let I check be the first integrals of delta check. These two, the number and the examples we'll look at, there'll be two first integrals here and two first integrals here. But the general theory, we don't care how many first integrals there are and how many first integrals there are here, as long as there's a sufficient number. Okay. Now, we're at this point of saying what the goal of the talk was today. Here is my manifolds that I want to construct. I'm going to start with my original manifold M, but I'm going to look at the submanifold defined by the level sets of this first integral. I'm going to look at another submanifold defined by the level sets of the other intermediate integrals or first integrals. Now, I'm going to restrict the characteristic distribution delta hat to its first integrals. I'm going to restrict this distribution to its first integrals, and then these are what we're going to call our Vecchio distributions. And the superposition formula for our original distribution M will be given in terms of so what we're going to do is we're going to build a superposition formula for the original distribution out of solutions to this. So give me an integral manifold here, give me an integral manifold here. I'm going to tell you, not today, but next time, how to build integral manifolds of the original distribution from this. So in terms of my goal from the very first day, we've done this, we've done this, we've done this, we've done this. I still have to do this part right here, and that will postpone till next time. But there's still lots of examples to look at. Oh, somehow things got a little bit mixed up here. Okay. So what's the simplest possible example you can look at? Woo. Sorry. Okay, here we go. What's the very simplest example you can look at? Is the wave equation. For the wave equation, here's delta hat and delta check. I can calculate the growth vectors for delta hat and delta check. The growth vectors are 2, 3, 4. That tells me that there's 3 intermediate integrals. You can obviously that y, q, and t are annihilated by this. So there are 3 intermediate integrals for each side. What's the restriction? The restriction of this to its level sets is you can see it right away. It's the contact distributions on J2R. So for the wave equation, these Vecchio distributions are the contact distribution on J2RR. And a classical theorem of Lie says that completely characterizes the wave equation. So let delta be a rank 4 hyperbolic distribution on a 7 manifold. If the growth vectors are for the characteristic distributions are 2, 3, 4, then delta is the standard distribution of the wave equation. Okay. We'll give a very easy proof of this from our general theorem, but I just want to stress how important these distributions are to our study. For the next example, I'll take Liouville equation. The Liouville equation is probably the most famous example of a Darboux integrable equation. I calculate delta hat and delta check. I calculate the derived flags. The derived flags are 2, 3, 4, 5. This means there are 2 intermediate integrals, which I've written down here. I restrict this distribution to the level sets of these, and we get this distribution right here. Okay. Partial x plus p partial u plus r partial p plus e to the u partial q partial r. So that's a rank 2 distribution on a 5 manifold. Right now, it doesn't look like anything familiar to us, but the derived flag is 2, 3, 4, 5. Well, we can check the Cauchy characteristics. So general theory tells us, that this has to be J3 of RR. Okay, and so this is why I spend a little bit of time going through this classical stuff on jet spaces and their characterizations. It's essential to understand this method of Darboux. In this case, we're taking the characteristic subsystems, we're restricting them to their level sets, and then we're identifying what those distributions are. Generally speaking, it's not too hard, but you need to have a good understanding of this classical literature. Here's a change of a diffeomorphism. X equals x, u equals log w, p equals w2 over w1. If you push forward this distribution here by this diffeomorphism, you get this. That's exactly the contact distribution on J3RR. So one of the things I like to do, I use my computer software all the time to first calculate abstractly what these distributions look like, and then I use the software to straighten them out and put them in standard form. I have one more example, and then I'm done for today. I'm sorry I went a little bit over. This is a very strange looking differential equation: uxx uyy cubed plus 1 equals 0. I have to say at this point, this is not the kind of differential equation that people in analysis would like to study. It's kind of strange, but this is a very interesting differential equation to study from the point of view of geometry of differential equations. It's not clear at the outset that this is a hyperbolic differential equation, but you can show that it is. And here I've written down what delta hat is. Delta hat is partial x plus 1 over t squared partial y. So there's a mixing of the independent variables here in constructing the singular or characteristic subsystems. And there's a similar formula for delta check. I didn't write it down. What's the growth vector for this? The growth vector for this is 2, 3, 5. So it's very different from what we had for Liouville's equation. When we were doing Liouville's equation, the side system, the characteristic system, had growth vector 2, 3, 4, 5, 4, 5. Now we've got this highly nonlinear equation. The growth vector is actually 2, 3, 5. Here are the intermediate integrals. The intermediate integrals are r plus s plus 1 over t, q minus st minus t x over t. So I want to restrict this system to its level sets. So I'm going to, I can't set this equal to 0. I'll get something singular. So I'll take s plus 1 over t, set that equal to 1. I'll set this equal to 0, and then I'll pull back my Pfaffian system to this. I get this rank 2 distribution on a 5 manifold. The coordinates are t, x, y, p, and t. Sorry, t, x, y, u, and p. So here are the 5 coordinates on this. Yeah, I listed them right here. You can go off and calculate the Cartan quartic for this. It turns out that the Cartan quartic for this vanishes identically, and which tells us by the theorem that we wrote down earlier that the Vecchio distribution for this is the same as the Vecchio distribution for the Hilbert-Cartan equation. Okay, I've prepared a maple. I think that's the end of it for today. One final example, the Goursat equations. For n equal to 2, the Vecchio distribution is just, sorry, I got this. Yeah, for n equals 2, the Vecchio distribution is Hilbert-Cartan. For n equals 3, it's this higher order Monge equation. For n equals 4, it's the next higher order Monge equation, and so on. These Monge equations all have maximal symmetry algebras within their natural classes. And so we find that the geometry of this differential equation of Goursat is very related to Monge equations with lots of symmetries. Okay, I think I'm going to stop there today. I hope I didn't insult you by doing too many simple things, but I wanted to stress the importance of this decomposition and then studying what the geometry is of these individual distributions. It's very interesting. The next step we have our distributions phi hat on our m hat. We have our distribution m check on m check. And the next step is to glue these together via some group action. And we'll describe what that group action is next time. Again, it's not difficult. It's quite easy to calculate. And the examples are actually kind of amazing. So that's what we're going to do. I'm going to stop there now, and we'll have some discussion and questions, and people can leave if they want. After that, if there's sufficient interest, I can I've prepared a Maple worksheet demonstrating the details of the calculations in this example. Okay, thank you very much.
Thank you, Aya. Thank you very much for your nice talk. It's been very clear, and you have presented everything in such a way that it's been wonderful. So thank you very much. So now, is there any question, remark to our speaker?
Ian, I have a question about the example we're looking at right now.
Yeah.
You said if you choose the level sets of the invariants poorly, you'll end up, what goes wrong if you, let's say s plus 1 over t equals 0?
I think what happens, you don't get the manifold, it's singular. I think the Jacobian, you get s equals 1 over t. I think, yeah, q then is 0.
Oh, I see. So
yeah.
it's just a bad level set. But
it's just
so
a
you
bad
could just
level
choose
set.
Most constants would work, is what you're saying.
Most constants are going to work, yeah.
Okay.
Yeah. It's like x squared plus y squared equals c, right? If you pick c equals to 0, you're in trouble.
Yeah.
I think that's the issue there.
So, any other question?
Yeah, I have a question. Maybe it would be more convenient to ask this on the next session, but in case I can make it, I can maybe use this time. I have been reading recently one of your papers with Mark Fels on precisely on the reduction of exterior differential systems.
Yeah.
In which, well, many of these constructions show up or in their dual part. So you have a derived ideal, and this is all cast in terms of differential forms. And I was wondering, these original distributions that you mentioned that have these bracket conditions in the dual language. So if these were given by kernels of some set of forms, because I I didn't see this in this paper I mentioned, and also when I followed up on a few of your further constructions later, which just to know what these were going, I didn't find it. So
yeah, so it's this inside of delta. So if we let theta alpha be the dual to delta, then the structure equations are d theta alpha. Sorry, these structure equations, these forms are going to split into two parts. They're going to split into one set, which satisfies structure equations like this. Oop. Oh. You're going to have so theta. So let's try and get some room here. So we have our distribution delta. We have the dual distribution, this, and I'm going to write these as forms theta hat and theta check. And I'm going to want structure equations. There'll actually be three parts. Basically, I'm going to have some forms that are going to look like this. Mod omega. So the structure equations for a hyperbolic system look like this. There's a coframe. Essentially theta hat, theta check, pi hat, pi check. There may be several of these forms. There'll be several of these forms. There'll be several of these forms. But the structure equations are going to look like this. So the structure equations at the top order at the symbol level decompose. So you're
Right.
getting
So I was
some
going to
form.
say that, Ian. It's the, it's the block triangular form of the symbol, basically, right?
Yeah, yeah. Is that Mark?
Yeah.
Yo,
Oh,
hey.
yeah. Hi, Mark. Okay. So it's this form here, and somehow this is a good point. Somehow I find it a little easier to describe what I'm doing with this formula. It's very natural rather than this formula. You have to say there's an adapted coframe such that da 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 da. So this is a little easier to work with at the get-go. And secondly, when I go to construct that group G, the Vecchio group, it's going to be constructed out of these brackets. So again, the vector field approach gets me to where I want to be a little faster.
yeah, okay, thanks. So there is a way, but maybe it's cumbersome or more.
Yeah,
thanks.
Yeah, and again, Mark and perhaps I should give a nod to my friends Mark and Tom. Mark and Tom have been working on the elliptic version of this, and again, you're going to have the distribution is now going to break apart into two pieces. But this would be kind of complexified, and again, it's not hard to say what elliptic Darboux integrability means at the distribution level. It's quite natural. Okay,
Yeah,
let me pull. Let's see if I can do this.
Okay, so any other question? I have one question, Ian, and I'm very curious, but I mean, my question may be more proper for the next talk. But there are some kind of differential equations called these systems. Yeah, they have a superposition rule, and this allows you to describe the general solution of differential equations in terms of a finite family of the same thing. Yeah,
right.
Here, right. If I understood properly, what you have is you have this delta, with this delta check, delta hat, yeah.
Yeah.
And then you have distributions generated by all of them that are integrable, that are the distributions p hat p check, yeah. And your main aim is to describe the integral submanifolds one into the other, so the solutions of one into the other, yeah. So I guess that there is some kind of way of describing the list system, the standard list system, by means of this approach. Yeah, have you tried?
Well,
anything?
I've been thinking about that because I thought that question might come up, and Mark's been thinking about that too. Mark, you want to say something? Certainly, we can see some Lie equations in this approach. That's for sure.
Yeah, indeed, there is another thing, because you have to start here describing the integral of the one Bayesian distribution in terms of another. I was also thinking, because it's something that some people in here are working on, that if you can make this a little bit more general, and considering delta to be the composition into three distributions, delta 1, delta 2, delta 3, and make some kind of stuff of the same time. I mean, you pick one of these parts, you generalize the minimal distribution integrable, and you pick up some conditions with intersection. Has this any sense? Could you, for example, mix this integrable distribution in terms of two another ones or things like that? Is there any sense?
So you want to do something
or...
like this: delta 1, delta 2, delta 3?
I think we can't see what you're writing.
Let's see. So somehow I've turned off my share. Yeah, I wanted to share this one. Let's see.
Yeah.
So this is the one.
I cannot see now. Maybe it's my problem. Yeah. Oh, now. Yeah.
Yeah. So somehow you wanted to do something like this, a triple decomposition.
Yeah, sure, something like that.
Yeah, we have some examples like this, and I think this shows up somehow. This shows up a little bit in another paper of Carton, 1911 paper, where he's studying PDEs in 3 variables, and somehow I think in that case there's one branch where you have some kind of triple decomposition like this, but the papers in that. But the integration technique in that paper, those equations are more of a kind of a parabolic flavor, and the integration method in that paper's not by the method of Darboux, but somehow it could be by the method of Darboux. So as I was saying, we really don't have. For hyperbolic equations and elliptic equations, we have this Vasio group construction. But for parabolic equations, we really don't know what to do there yet. I don't think that's worked out so clearly.
Yeah, I understand.
And what happens, you're going to see in the next lecture, is we trade off the derived flag for delta hat against the derived flag for delta check. So it's the interplay between these two flags, which is kind of important, which will be what we're going to talk about next.
Okay.
So hey, Ian.
Yeah.
So when there was that question about equations of Lie type, that stuff's going to show up a little bit in the next lecture, would be my guess.
Yeah.
A little hard to say much about it without just saying a little bit more about like the Vasio group and so on. Right.
Sure, because in this is maybe the one of the interesting things to me, how to find this G group and how it appears.
Right.
And just one comment, because also, for example, for my colleagues, one of the interesting things is when this distribution you have, they are somehow spanned by means of Hamiltonian vector fields of certain type. A comment is that in that case, well, for listed it works that the description of solutions can be easier, adding some kind of symplectic or Poisson structure. I don't know, but well, let us say it this way: I'm looking forward to hearing your next talk in Portugal. Will be very interesting. Really interesting. About the Maple,
Let me pull that up and let me just see what we've got there.
Yeah,
Let me
it's
pull it up.
if you don't mind, I mean, if someone want to leave, because this is a subject in the university, they can leave. It's not obligation, but for research for my colleagues who are working with me, it can be interesting to take a look.
So let me see if I can bring this up. Yeah.
Could I throw one other thing about Lie type in
Sure.
there?
Yeah.
The prescribed Darboux invariant, say,
Mhm.
right?
Right. So let's talk about that for sure next time.
Okay.
Yeah. Okay. So let's see if I can. I need to share a screen, and the one I want to share is this one. Yeah, this one here.
Okay.
Okay. Can you guys see this maple screen?
Yeah, sure. Yeah.
Okay. Maybe I'll blow it too big. Do it this way. It's this. Move this thing if I can. And let me blow this up a little bit. Good.
Yeah, great.
Okay, so this is just kind of a very quick introduction. So this differential geometry software package has been going on. I've been working on this for a long time. And I would say it's been very helpful for me and my colleagues. And it's a symbiotic relationship. We use the software to do research. We then use the research to improve the software. And so because the software has been driven by research in geometry of differential equation, it is really quite good software to use for the kinds of things that we've been talking about. There's a main package. There's a tensor package, there's an extensive Lie algebra package, there's a differential systems package, there's a jet package, there's a group action package, there's a library of databases of solutions to Einstein equations and Lie algebras, and then there's another package which contains various specialized applications. So a long time ago, this was integrated directly into Maple. Now you can get the most current release versions from our website, or you can just type in differential geometry software and it'll take you right. It should appear fairly high in your search, and you can download the software from there. It will run. This software should run on just about any version of Maple that you have, even fairly old versions. So for the demonstration I prepared today, I'll just do a couple of examples. Okay. So I'm going to load in the packages. I'm going to show you this one here. So you can see that I think there's over 100 commands inside the Lie algebra package. It's got a lot of stuff in there. All the stuff about Weil groups, a lot of stuff on parabolic geometry because I've been working on that. Constance theorem for simple Lie algebras, Lie algebra cohomology. It's got a lot of stuff in there. You'll see an example of this in a minute. Okay, we have an exterior differential systems package. That's kind of a smaller package. That's got some stuff for calculating symmetries of differential systems, integral manifolds, different things as well there. The tensor package is also a very big package. Okay, just to give you a flavor of how this goes, I wanted to start with this very famous Hilbert-Cartan equation. So as we saw in the talks, we need a 5-manifold. So I use this environment command, DG environment manifold, to create a 5-dimensional manifold. X, U, U1, U2, and Z are my coordinates. And then one of the important things about this differential geometry package is you just type in the vector fields that you want exactly how as you think they should look. And then I'll type those in. Oops. Didn't run this. And there's my rank 2 distribution in a 5 manifold. Let me have something here.
It looks better than Mathematica for sure.
Let me do something here. Let me hide. Just a second. Well, I want to undo output. Let's try that. Okay. Okay. Well, we'll leave it as it is. Let me just go back and do. Okay, so there's our distribution right there. There's, I think, something like 15 different environments. There's a manifold environment, a jet space environment, a homogeneous space environment, a Lie algebra environment, an algebra environment. So there's lots of different computational environments that you can initialize. And I think what makes this package useful is that all these different environments talk to each other. So you can bounce around from working on a manifold to doing a Lie algebra calculation just pretty effortlessly. And I think that's the point that I want to demonstrate here. So here we have our distribution. The command infinitesimal symmetries of EDS is one of the commands that people like a lot in this package. Boom. Very quickly calculates all the symmetries of this differential system. It turns out that there are 14 symmetries. So here are the vector field symmetries. Let's look at one of them in some detail. So here's the first one here. That's a pretty complicated vector field. Let's check that it's actually working. So I'm going to take this vector field, which I claim is a symmetry of the differential equation, apply it to this vector field here by Lie differentiation. I get this vector field. And if this is a symmetry, then this Lie derivative should be a linear combination of the vector fields in the distribution. And so we use this get components command. Is this vector field a linear combination of the vector fields in my distribution? The answer is yes. And I can do that with this get components command. So this vector field is this function times delta 1 plus this vector field times delta 2. Okay.
If you allow me to say, it's very good. Have you tried more difficult distributions? Because,
well, we've done thousands of distributions. Every day I'm doing.
Yeah.
Every day I'm doing something with this. So this was just the trick. So what happens is you calculate the defining equations for the distribution. It's a large overdetermined system. And Maple's very good at solving large overdetermined systems of linear PDE. Sometimes it will hang. You'll hand it something and it will run and run and run. You'll never get an answer. Yeah. Well, when that happens, you need to know the tricks. And it's pretty unusual for someone to give me a reasonable distribution or something like that, for which I can't find the symmetries. Sometimes if it fails, I'll ask Maple to give me the polynomial symmetries, which are defined by polynomial vector fields.
Sorry, I have to interrupt the business. It's very interesting. We will check it and we will let you know.
Okay, send me your example. Okay, send me an example of something you want the symmetry for. Okay. Now we've got the infinitesimal symmetries. I'm going to switch environments. I'm going to go to the Lie algebra, the abstract Lie algebra defined by these symmetries. And then here's the multiplication table. It's kind of big. Let me shrink it down. Let me shrink this down a bit for a second. So there it is. It's a 14-dimensional Lie algebra. E2 bracket E1 is E7. E2 bracket E8 is E10, and so on. So there is the structure equations for this 14-dimensional symmetry algebra. I'm going to hide that now, and then we're going to go back up to larger size. Okay. Now let's do some properties of this. The first thing we'll do is we'll ask, is this symmetry algebra of the Hilbert-Cartan equation semi-simple? And the answer is yes, it is semi-simple. Let's calculate the Cartan subalgebra. There's the Cartan subalgebra. And now a huge amount of software has gone into building this classifier. Let's classify this semi-simple Lie algebra. And the computer tells us that this is G2. And there's the signature of the Killing form. So that we can say that the symmetry algebra of the Hilbert-Cartan is the split real form of the exceptional Lie algebra G2. Okay, so that's sort of well known. Goes back to Cartan, of course. But the important point here is how effortlessly we were able to do this on the computer. Just off we go. There are distributions whose symmetry is the exceptional Lie algebra F4. So even something big like F4, the software handles that without too much difficulty. I'm going to store these values for a minute. So for something I want to do next, I want to reorder this basis. Okay. Let's go now to our equation. Let's see if I can just. Where is that thing that you hide? Remove the output. Let's see if we can remember where that is. Edit, undo output. Should be. Tom, you remember where that is? It's a little easier if I can just no, I don't remove the section. It's okay. Okay, so now here's our equation that we were talking about. Okay, RT cubed plus 1 equals 0. So I'm going to solve that for R and write the equation as R equals 1 over 3t cubed. Okay. Here's the Pfaffian system. du minus p dx minus q dy dp. And now here's R, so I put in the value for R. And S and T are my remaining coordinates. And here's my dual distribution. So here's my rank 4 distribution. Okay. And now I want to show that this is hyperbolic. And so I need to calculate delta hat and delta check. Not so easy to do, but there's a command called singular vector fields, which will do the job. So a vector field is the delta hat and delta check are singular vector fields in the sense that if you bracket them with the distribution you start with, the growth vector is as small as possible. So there's an intrinsic way of characterizing this decomposition. So here is my hat delta. Here is my check delta. I claim that this is a hyperbolic decomposition. So what I should do is I should take the vector fields in hat, the vector fields in check, Lie bracket them together. So when I do those Lie bracket condition calculations, Lie derivative conditions calculations, I'll get 1, 2, 3, 4 vectors from all the possible brackets. And now I want to see if these vectors are linear combinations of delta. And it is, so I've checked on using the computer. I've checked that the equation RT cubed, 3RT cubed plus 1 is a hyperbolic, defines a hyperbolic differential system. Well, we want to calculate, let's do this. Let me open up some room here. Oops. Let me do a derived flag. Of hat delta. I'll call that df. And actually, I don't want to look at the entire flag. I just want to look at the growth vector. See if this works. Yeah, so as I said in the presentation, the growth vector for the singular distributions or at the delta hat for this equation is 2, 3, 5. I'm on a 7 manifold, so the terminal derived flag is 5-dimensional. That means there's 2 first integrals. So I can tell right away, without calculating what the intermediate or first integrals are, I know just from this numerology here that the system is Darboux integrable. So I want to stress that. Sometimes you might have something that's so complicated you can't find the first integrals, but you can also find out how many there are. So there's a command in the differential systems package called first integrals, and there's the first integrals for the hat system, and here's the first integrals for the check system. Okay. In the worksheet in the talk, I said I want to go to the level sets. So here's my level. Now I'm going to define a new manifold. It's a 5 manifold. I'm going to define the inclusion map. So the inclusion map from the level set into the 7 manifold, that's a mapping from hat M into M7. So the inclusion map is, what I'm going to do is I'm going to take this equation and this equation. I'm going to solve them for S. So I'm eliminating S and Q from these equations. This is what I get here. I'm going to pull back that to the level system. And here's what I had on the worksheet. This is my Vesio distribution for RT cubed. Okay. Again, it has derived flag 235. There is software available for computing the growth vector, but let's just take this somewhat complicated looking differential system and calculate its symmetry algebra. Done very quickly. And again, the number of symmetries is 14. So Nolan, you wouldn't see this anywhere in the literature, but this is some other very strange looking realization of the Hilbert-Cartan equation. I don't want to spend too much time on this, but whoops, sorry.
Really, for my colleagues and myself, it's far from enough. I mean, it's really very, very interested, and I almost finished preparing an email with an example for you. I mean, we will check it by ourselves. We will download the thing, and we'll find that they can be interested.
Let me just end on one point. So with the software, you're able to find the explicit diffeomorphism. I won't show you how I did it, but here's a transformation from one coordinate system to another coordinate system. If I apply this transformation to my distribution and clean it up, it brings it exactly into the form of the Hilbert-Cartan equation. So I started off with this thing. I did this complicated diffeomorphism that I found using the software, and it straightens it up. So not only do we know from abstract theory that this distribution, not only do we know from abstract theory that this distribution is a Hilbert-Cartan equation, but I actually gave you the coordinate transformation, which aligns it. How did I do this? Well, what I did was I had the two distributions. They each had a 14-dimensional symmetry algebra. I aligned the symmetry algebras and found the diffeomorphism mapping one symmetry algebra to the next, and that does it for us. To align the symmetry, to align the two symmetry algebras. There's a command that automatically will do that for you. It's called finding the isomorphism between two semi-simple Lie algebras. Very easy to do using what's called the Chevrolet basis. So there's a lot of power here at one's disposal for doing all kinds of things. So that just gives you a little flavor of the software and what it can do. And we'll see next time that in order to calculate these Vesio groups, the group linking the two distributions together, for simple examples, you can do it by hand, but for more complicated ones, you've just got to use the computer. Okay, thank you very, very much.
Thank you indeed very, very much. And it's been very, very interesting. And I guess that it will be very useful to us. So looking forward to see you within 2 weeks. Yeah.
Okay, 2 weeks.
At the
yeah.
same time. Yeah.
Okay, great.
Thank you, Ian. Thank you, everyone. And let us thank again because it's very great. Thank you for your time. Really. Have a good day, and we will send you an email. Okay, Ian?
For sure. I give it. We give it a try.
Time.
Okay.
Yeah, sure.
Okay.
It's. I have seen worse things in this in your calculations, so maybe it will work out. Yeah, as you said. Thank you. So, and then see you everyone in a week. That we have 2 talks. One by Tempesta from the ISEMAT, and another one by Michalina that was postponed due to a problem in the university. You know what happened a week ago. So see you in a week. Thank you.